Gas is pumped into a spherical balloon at a rate of 5 centimeters cubed per minute. How fast is the surface area increasing when the radius is 15 centimeters? So let's think about this real quick. We know the rate, okay, at which this gas is being pumped into the balloon is 5 centimeters cubed per minute. Now, if you're confused about what is this rate that they're giving you, look at the units here. This is centimeters cubed. That's going to be a change in volume. And this says per minute, that's going to be change in time, right? Minute is a unit of time. And so that's going to be positive 5 centimeters cubed per minute. You know it's positive because the gas is being pumped into the balloon. That balloon is expanding, so it has to be a positive, positive sign, okay? Now, we're also looking for how fast is that surface area of the spherical balloon increasing. So we're looking for dA over dt. Okay, we don't know what that is, when the radius is equal to 15. So let's think about this. Do we know a formula which ties these kind of variables, this v, this a, and this r together? And unfortunately, at least in the case of spheres, that formula doesn't really exist, okay? But what we do know is two different formulas. We have volume of a sphere is equal to 4 over 3 pi r cubed, and we also have this other formula, which is the area of a sphere, the surface area, is equal to 4 pi r squared. So now you're wondering, which one should we take the derivative of? Okay, which one should we differentiate with respect to time? And I guess the obvious answer would be, well, if I want to know what dA over dt is, I should take the derivative of the one that has area, right? That's going to pop out with dA over dt. So let's do that, okay, on this right side here. So it's going to give me dA over dt is equal to 4 pi, and this is going to give me 2r dr over dt. Okay, now this is what we're looking for, so it's okay that we don't know what that is. This radius we know, right? We're looking for d over dt when radius is 15, so we can plug that in. But this dr over dt bit, we don't know what this rate of change is. So that kind of gets us stuck in this kind of process here. But luckily, we still have this other formula here, and we know something about the rate of change of volume. So we can use this information to find something about the rate of change of my radius. Okay, so let me draw a little line here. And let's take the derivative of this left equation here. This is going to give me dv over dt is equal to 4 over 3 pi times 3r squared dr over dt, right? And here I guess these 3's will cancel out. So we can kind of simplify this as 4 pi. And r squared, well, we're looking for dr over dt when radius is 15, right? So we can plug in that 15 here, 15 squared dr over dt. And we can plug in this dv over dt bit. This is just going to be 5, right? And so now, if we divide both sides by 4 pi times 15 squared, that's going to give you your dr over dt, right? And so that's actually just going to come out to approximately 0.00177. So now we know what dr over dt is. So let's just plug it all in then. Okay, we don't know what this is, so let's just leave it on the left side here. We've got 4 times pi times 2 times 15 times 0.00177. And that's going to come out to 0.67 centimeters per minute. Okay? And that's the answer for question A. Now on to question B here. Okay. Gas is escaping a spherical balloon at a rate of 3 centimeters cubed per minute. How fast is the surface area changing when the radius is 12 centimeters? So once again, they've given us this change in volume per change in time, right? That rate of change, that's going to be dV over dt is equal to, now the gas is escaping, so it's going to be negative 3 centimeters cubed per minute, right? That balloon is shrinking as that gas is escaping. Now, we're asking for how fast is the surface area changing. So once again, we're looking for dA over dt. Okay. when r is equal to 12. All right, so let's write our two formulas again. We've got v is equal to 4 over 3 pi r cubed, and we've got a is equal to 4 pi r squared. Now let's differentiate here. So on the right side, on the left side here, we've got dA over dt. And on the right side, we have 8 pi r dr over dt. And once again, we're stuck, okay? This is what we're looking for, okay? That's great. We don't know what it is. That's fine. This r here, okay, we're looking for when r is equal to 12, so we can plug that in later. But this dr over dt, once again, I don't know what that is. But I know this rate of change, so I can use the information here to help me solve for that information, okay? So let's draw this line once again and differentiate this equation. So that's going to give me dv over dt is equal to 4 over 3 pi times 3r squared times dr over dt. And once again, these 3's cancel out, and you're going to get, well, on this left-hand side here, that's negative 3, right? You got 4 times pi times, and instead of r squared here, because we're looking for dr over dt when we're looking for d over dt when r equals 12, I can plug in 12 right here, okay? And we've got this. So now we just divide both sides by this bit in the front here to isolate that dr over dt. So that's going to be negative 3 divided by all this, 4 pi times 12 squared is equal to dr over dt. And this is going to come out to approximately negative 0.00166. Okay? So now we've got that as well. We just have to plug these two things here, this r equals 12 and this dr over dt equals negative 0.00166. And that's going to give you your dA over dt, okay? So dA over dt is equal to 8 times pi times 12 times negative 0.00166. Okay, and that's going to come out to approximately negative 0.5. And your units here are centimeters squared per minute.